In the beginning there was the point, the building block for all that comes. Next came the line. Next there was the plane. Finally there was space, the three-dimensional space surrounding us right now. By removing axes, our shape gradually shrinks, and eventually becomes a point, like it was in the beginning. Before we continue any further, let me first make a few definitions. Let us define an n-cube to be a cube-like object in n dimensions, with congruent line segments and only right angles. For example, a cube is also known as a 3-cube, and a square is a 2-cube. Let us also define a traversal tunnel through a figure to be an empty space in the figure that has at least 2 openings, which may be on the same face. For example, using a cookie cutter on a lump of dough creates a cookie-shaped traversal tunnel. Let us first look at these 4 dimensions. The 0th dimension only contains the point, an immutable object with 0 properties. The first dimension contains the line. Lines can vary in only their length. In the second dimension, shapes can have multiple sides and can have gaps without the shape being separated. Finally, there is the third dimension. The third dimension is the first dimension in which a traversal tunnel can exist without separating the shape. I have observed that the net for an n-cube consists of 2 n faces, each face being an n-1 cube. For example, a 3-cube contains 6 2-cube faces. Now, how does a tesseract contain 8 cubes? Only 2 are seen. The answer is that each of the 6 frustrums surrounding the inner cube is actually one of the distorted cube cells. Therefore, there is 1 small cube, 1 large cube, and 6 distorted frustrum cubes. This is an animation of a cube growing along the w-axis, becoming the 4th dimensional tesseract. Note how the outer cube does not change in size, but the inner cube shrinks and the frustrums increase in size. The tesseract is capable of rotating along 6 axes. 3 of these are in our dimension, as demonstrated in this animation. There are another 3 axes in which, when a tesseract rotates about them, it appears to swap the position of the different cubic cells. So, one of the frustrums becomes the inner cube, and another frustrum, specifically the one across, becomes the outer cube. This is shown in this animation. Another discovery I made is of the resemblance between higher and lower dimensions, a phenomenon I call the reduced dimension representation. A cube, when shrunken to a sufficiently small volume, begins to resemble a point. This is because a cube is uniform in length on all of its sides, as far as the 3 dimensions in which we concern ourselves. A line and a plane do not resemble a point as much because they do not have the same length in all 3 dimensions. Therefore, when represented correctly, a tesseract resembles a line with cubes as vertices, a pentaract or a 5-cube resembles a plane, and a hexaract or a 6-cube resembles a 3-cube, which represents a 0-cube, or a point. Therefore, an n-cube will resemble an n-mod 3-cube. Picture a scene in the second dimension. Now imagine a 3D object on one side of the wall. Say now that I want to move the object to the other side. Instead of going around the wall, we could instead move the object up into the third dimension, over the wall, and back down. To a 2D object in this scene, the 3D object will have disappeared and reappeared sometime after on the other side of the wall. Now picture another 2D scene. We have a 3D camera and a 2D camera in a 2D scene. There is now also a 2D object on the plane, with 1 hole in it without any openings to the side. At any one point in time, the 2D camera can only see a one-dimensional representation of the object, and cannot see the hole, assuming this object is opaque. However, by moving the 3D camera up, we are able to see the entire object at once, and also perceive the hole. Similarly, if I presented you with a sphere, you would not be able to tell whether or not the sphere is hollow just by looking at it. Also, a 3-dimensional camera takes 2-dimensional images, because even if it can see through objects, the color behind the translucent object shows through, therefore still maintaining a 2-dimensional capture. So if I were 4-dimensional, that means that I would be able to see all of your insides. Not that I would want to anyways. Now I will introduce what happens when an n sphere passes through a lower dimension. In the story Flatland, written by Abbott, pseudonym A Square as a pun on his double name, a sphere passes through an unsuspecting two-dimensional world. So as the sphere becomes tangent to the plane, a point is perceived. As the sphere moves inward, the point expands and becomes a circle with equal radius to the sphere. Then the sphere gradually begins to move outwards again, and the circle shrinks until it becomes a point again, and then is never seen again. Finally, I will talk about the mathematical properties of an n-cube. An n-cube, as stated before, is an n-dimensional compact closed convex figure with 2 to the power of n vertices. The number of k cubes on an n-cube, assuming k is an integer less than the integer n, is equal to 2 to the power of n minus k times n factorial divided by k factorial times n minus k factorial. This formula is complicated if you listen to me, so look at the whiteboard. Note that the number of k cubes in an n-cube if k is greater than n is always 0. This formula also equals 2 to the power of n minus k times n choose k. For example, to count the number of faces, 2 cubes, on a 3 cube, one will calculate 2 to the power of 3 minus 2 times 3 factorial divided by 2 factorial times 3 minus 2 factorial, which equals 6. I'll do the calculating for you. Using this formula, we can determine that the number of 5 cubes on a 7 cube is 2 to the power of 7 minus 5 times 7 factorial divided by 5 factorial times 7 minus 5 factorial. Again, I'll do the calculation for you. That equals 84. Now we're counting the faces of a cube in math class. The number of free axes of rotation is equal to half of the number of planes in the n-cube. For example, there are 6 planes on a 3 cube, and there are 3 axes of rotation on the cube. On the tesseract, there are 12 planes and 6 axes of rotation. This calculation does not apply for dimensions lower than 3. A plane has 1 rotation, as with a line, and a point has 0 rotations. Alright, so that is the end of this video. I hope you enjoyed this video, and I hope you also learned something new about multiple dimensions. Have a great day, and I hope to see you soon sometime.